In this lesson, we're going to introduce you to Taylor polynomials. Polynomials are used to approximate functions because they're easier to work with, easier to evaluate, to take the derivative, and to integrate. But for now, we're just going to develop how to get a Taylor polynomial. Right here, you see a picture with a cosine curve, and we've got a series of Taylor polynomials sitting here, and you'll notice this one, where it's just a constant function, is really only a good approximation near the y-axis. The next one, the approximation gets a little bit wider, and here we've got a 4th degree even wider, and our 6th degree even wider. And so we can see as we increase the degree, we increase how well it'll approximate the function. We're going to start off with something you're very familiar with from Calc 1, which is to find the equation of a tangent line. The tangent line is really a 1st degree Taylor polynomial. So we're going to go ahead and write the equation of that tangent line. Y minus f of a equals, I need my slope at a, so that would be f prime at a times x minus a. And if I simply solve this for y, and get f of a plus f prime of a times x minus a, I've actually written a 1st degree Taylor polynomial. This is an approximation for the curve, and we can see on the graph that it's a pretty good approximation for a small area around the point a, f of a. But of course, if we move away from that, the approximation is not quite as good. Now, when we write Taylor polynomials, we're going to use a p to mean polynomial, a subscript of 1 because it's 1st degree. It is 1st degree because the highest power on x is a 1. And we're going to say that this function is approximately equal to f of x. And we can see those values are best near a, and they get much worse as we move away from a. All right, so now we can see that our tangent line is good right near a, f of a, but boy, we wish it could be better a little farther out. And so the improvement on that would be to move to a 2nd degree Taylor polynomial. So in our 2nd degree Taylor polynomial, we're going to have another point that's the same. Remember, in a 1st degree, we always need the point, a, f of a, and we also needed the 1st derivative, f prime of a, which basically said that our tangent line has the same point and the same slope as the curve. In a 2nd degree Taylor polynomial, we're going to go one step farther. Not only is the function and the curve going to share a point, and they're going to have the same 1st derivative at that point. In addition, they're going to have the same 2nd derivative at that point. All right, we're going to get rid of that highlighting and move on to a general equation for this polynomial. So we need a 2nd degree polynomial, and I don't know what any of the values are yet, so I'm just going to use c, meaning constant. So c sub 0 plus c sub 1 times x plus c sub 2 times x squared. So all I've done here is write a general 2nd degree polynomial, and later on I'm going to write different values in for c sub 0, c sub 1, and c sub 2. I can see that I'm working with 1st and 2nd derivatives, so I'm going to go ahead and calculate the 1st derivative of this polynomial. That's going to be 0 plus c sub 1 plus 2c sub 2x. And we also talked about needing the 2nd derivative, so I'll go ahead and do that. 0 plus 0 plus 2c sub 2. Now, these values we had over here to the right, I want to be able to relate to the polynomial. So I'm going to actually take right here and put 0 into the very first polynomial I have here. So when I plug in 0, all the x's turn to 0, and this ends up equaling c sub 0. I'm going to do the same thing for the 1st derivative. When I plug 0 into the 1st derivative, I get c sub 1. And then when I go into the 2nd derivative and I plug 0 in there, I get 2c sub 2. Now, having all of this is going to allow me to take this general polynomial and write it in terms of f. So remember, we are approximating f of x with a polynomial that's degree 2. So I've got my curvy equal sign to say they're not exactly equal. And this polynomial equals. So in the first term, I had c sub 0. And if I go off to the right, I can see c sub 0 actually equals f of 0. So I'm going to write it with f of 0. Next, I come over here for c sub 1, and I can see that off to the right, I have c sub 1 here, and c sub 1 equals f prime at 0. So I've got f prime at 0 times x plus, for c sub 2, I come down here to the third line, and there's c sub 2. And well, it doesn't exactly equal the second derivative at 0, but if I divide by 2, then c sub 2 equals the second derivative at 0 divided by 2 times x squared. And now we have written a second degree Taylor polynomial that approximates our function f. Now, we haven't done enough to actually see the full pattern. So what we're going to do next is go to a fourth degree. And this should go a little faster because you've seen it already once. So here we go, the fourth degree. And you can see on the right-hand side, I have all the values that have to be true to get a fourth degree Taylor polynomial. Not only do they share the same value at 0, they share the same first derivative at 0, the same second derivative at 0, the same third derivative at 0, and finally the same fourth derivative at 0. So we're going to do the same sort of thing, but the polynomial is going to be a lot bigger. This is p sub 4. So we're going to have c sub 0 plus c sub 1x plus c sub 2x squared plus c sub 3x cubed plus c sub 4x to the fourth. All right, so we're going to start taking derivatives. So p sub 4 prime equals c sub 1 plus 2c sub 2x plus 3c sub 3x squared plus 4c sub 4x cubed. All right, let's keep going. Second derivative equals 2c sub 2 plus 3 times 2. There's a reason why I'm doing this, so I'm not going to actually multiply it out to 6. 3 times 2, c sub 3x plus 4 times 3, c sub 4x squared. All right, on to the third derivative. We get 3 times 2 times 1, c sub 3 plus 4 times 3 times 2, c sub 4x. And then the last one, the fourth derivative, equals 4 times 3 times 2 times 1, c sub 4. All right, I'm going to take all of that and shrink it down. That was quite a lot of stuff. We'll group it as well. All right, so we've got it grouped, and we're going to just make it at a more manageable size, and we're going to bring these in now. So in our first line, we're going to plug in 0, and when we plug in 0, we get c sub 0. In our second line, when we plug in 0, we get c sub 1. In our third line, when we plug in 0, we get 2c sub 2. Now up to here, you should notice these are the exact same things we had on our previous one. Okay, now things get a little more interesting. We plug in 0 on this next line, and we get 3 times 2 times 1. Wait a second, that's just 3 factorial. So 3 factorial c sub 3. And then on this next one, we can see that, wait, that's 4 factorial c sub 4. In fact, you'll see that this really is 2 factorial, right? And we could write this as 1 factorial. And what the heck, let's call this 0 factorial c sub 0. Now we've got a pattern working all the way through. So now we're going to go ahead and write that Taylor polynomial just like we did before. So this is approximating f of x. It's a fourth degree polynomial, and we want to write it in terms of f. So for c sub 0, we see that c sub 0 equals f of 0. So we have f of 0 plus, for c sub 1, we have f prime at 0 times x. For c sub 2, we come over here just like before. We're going to have to divide by 2 plus f double prime at 0. And I'm going to divide this by 2 factorial plus. For c sub 3, we can see that to solve for c sub 3, we need to divide by 3 factorial. So f triple prime at 0 over 3 factorial x cubed. I just noticed that I was missing x squared over here, so we'll get that fixed up here. X squared. And then our very last one, for c sub 4, we come down here and we see we'll have to divide by 4 factorial plus the fourth derivative at 0 over 4 factorial times x to the fourth. All right, we're going to leave it at that and put the general form in a, no, we'll go on. We're going to put in a general form. So based on what we just saw, the general form for a Taylor polynomial goes like this. Oops, let me try that again. F of x is approximately p sub n, which equals f of a plus f prime of a times x minus a plus f double prime of a times x minus a squared over 2 factorial plus dot dot dot, and here's our general term. The nth derivative at a times x minus a to the nth all over n factorial. Now, what we were doing a moment ago was all at 0. So let me go down to the Maclaurin polynomial. Maclaurin polynomials are always centered at 0. Always centered at 0. Our Taylor polynomial is centered at a, so that can be any number. So for our Maclaurin, it's going to look like this. F of x is approximately our polynomial, and we have f of 0 plus f prime at 0 times x plus f double prime at 0 times x squared over 2 factorial plus dot 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 plus the nth derivative at 0 times x to the n all over n factorial. That's the end of our introduction to Taylor polynomials.